All right, welcome to this video for Chem 161, where we'll look at the Bohr model for the atom. All right, so Bohr's model suggested that there are only certain electron energies that are possible in the atom. So that is to say that our story for the atom, if we rewind to the planetary model for the atom where we have a nucleus, and we now can explain why certain orbits are only allowed given the wave-like properties for electrons. So we remember a standing wave model where only certain circumferences allow the integral repeats for the wave pattern to exist on the ring, that is the orbit for the electron. We'll see here that in the Bohr model, we label these allowed orbits with a number. So this would be the n equals 1 orbit. The next one would be the n equals 2 level. And then the next one would be n equals 3. And these are the certain energies. There's an energy associated with these energy levels, and these numbers 1, 2, and 3 we'll use throughout the course, and we'll refer to these as the principal quantum number. So number 1 is an option for the principal quantum number, number 2 is also an option for the principal quantum number, and number 3 is another option for this principal quantum number. We have the idea next in the Bohr model is that not only are only certain electron energies are possible, but we have the idea for quantized energy from our earlier thoughts here on photons. And so we'll say here that energy of the electron must be quantized. Okay, so only certain energies are allowed given that they can only exist on certain circumferences around the nucleus. Okay, and so the consequence here is just as said, is that the orbit radii corresponds to definite energy levels. Okay. And the last thought here is that we're going to allow electrons to switch between these options, but it's going to require energy. Just like if you are to raise a book from the floor to the table, you have to apply energy to do that, to change the potential energy of a book on the floor versus the table. Energy has had to be input into that book to get it at a new gravitational potential level. So we'll say here that energy is emitted or absorbed by the electron as the electron changes from one energy level to another. Okay, so that is to say, it's entirely possible that an electron may reside out here on the n equals 3 case, and it could fall to another discrete and allowed orbit radii, nothing in between. And in falling to this case, we expect energy to be released from the atom. Okay, so we typically show this as energy being released in the form of a wave. So this squiggly line is shown on purpose because the energy released here is going to be a photon, a packet of energy. So we'll say that this is a photon is emitted. And of course, the energy of that photon corresponds to Planck's constant times the frequency of that wave. Okay. So with those ideas in place, we can better explain some of the experimental observations that we have for ionized gases. So if we look at the hydrogen atom, consider the ionized form of hydrogen gas, and there's a separate video to show you this. I encourage you to look at it. You will see here that we observed 4 lines as ionized hydrogen gas relaxes. So that is, we see 4 discrete types of photons as electrons relax within the ionized hydrogen atom. Okay, so here you can see them. 1, 2, 3, 4. 4 discrete lines. You can see the color of them placed on a scale that here is speaking to the wavelength. So this is a wavelength scale extending from just under 400 nanometers all the way to just above 750 nanometers on this X scale. And so there are only 4 discrete lines emitted from the hydrogen atom. And these lines and their colors are shown here. So the red photons that are emitted are almost 650 nanometers. The cyan photons that are emitted are almost 500 nanometers. Those that are a little more blue are about 430 nanometers. And then there's another photon that's more violet, and it's just about 410 nanometers in wavelength. These emitted photons are shown here, where a model that applies these ideas from Bohr to an energy scale. So here's our energy scale increasing as we go up the slide. So the n equals 1 closest to the nucleus would be at the lowest energy point. So this corresponds to this energy level. An electron existing there would be on the n equals 1 principal quantum number level. The next one, n equals 2, is the next orbit out here. And n equals 3 is up here. So how do we explain the type of photons that are emitted? Well, they occur from excited electrons, electrons that are high in energy, and they need to fall down to a lower energy situation. And energy must be conserved. So if the energy goes from a high situation if the electron goes from a high electron orbit to a low electron orbit, it is dropping in energy. A photon must be released to balance the energy situation for that transition. Okay, so that's why we cartooned that emitted photon there. So the photons that led to the red, the cyan, the blue, and the violet photons that we see in the emission line from hydrogen correspond to transitions that all end, that is, finish with the electron at the n equals 2. So all electrons will end up on the n equals 2 orbit. Okay. Where do they come from? Well, they have to come from higher energy levels to emit photons of energy that is positive. So the red photons come from n equals 3 down to n equals 2. Those would be the red photons. The green photons come from n equals 4, the fourth orbit, down to n equals 2. Okay, the kind of cyan photons come from the n equals 5 and drop down to n equals 2. And finally, the blue photons, which are highest in energy, lowest in wavelength, come from the n equals 5 down to 2. Okay? I'm sorry, 6. 6 down to 2. 6 down to 2. Okay, so that explains the 4 transitions and the 4 photons that come out of this. Okay, as you can see, those photons end up with wavelengths that are in the range of 400 to 800 nanometers in wavelength, and our eye can see them, and which is why we're able to see these in a glow discharge experiment with a prism to spread the emitted photons to a different position according to their color. Other photons can be emitted that we can't see with our eye. So that is not the Balmer series, which is characterizing photons that can be seen with the naked eye, visible light type photons, but those that are much higher in energy correspond to the ultraviolet range, where our eye cannot see and would actually undergo damage if we did inspect these types. These involve transitions that end at the n equals 1 orbital, okay, or orbit situation. So electrons would be falling from higher levels to n equals 1 to emit these photons. All of these transitions would be UV emitting. Okay, and then another series is the Paschen series here, where they end at the n equals 3. And so here the energy distances are quite small, and so the type of energy associated with these transitions is very small. These are infrared photons that, again, our eye cannot see, but are very low in energy and very high in wavelength. Okay, and so with those ideas, to try to quantify all those transitions and explain what was happening, we have the Rydberg relation and constant. Okay, so that is to help explain electrons and the change in energy of those electrons. So we'll use a delta to indicate change and change in energy of these electrons in Bohr's atom. We'll also have the idea of the Rydberg constant. Okay, so this equation tells us that the energy of the photon emitted, which represents the change in energy for the electron as it relaxes, so this delta E goes as negative the Rydberg constant, a subscript h on that, times 1 over the final principal quantum number where the electron ended up. We'll put a square on that, minus 1 over the principal quantum number for where the electron started, and we'll put a square on that. So we'll use lowercase f to indicate final position of the electron. Okay, so this is final energy level of the electron. And then we'll use the lowercase I, the subscript I, to indicate the initial energy level. of the electron. Okay. The Rydberg constant, RH, the Rydberg constant, RH value, is equal to 2.179 times 10 to the minus 18 joules, discrete joules. This should make sense to you. We're expecting energy units to be in joules. Everything in the parentheses is unitless. This is simply numbers describing where the electron started and ended up. So these are unitless kind of address type information. And so the Rydberg constant finally gives us energy units of joules as we expect. Okay, so let's take a look at an example maybe to see how this works. So we'll describe a nucleus here, and we'll put some allowed orbits around it. Okay, so the closest one is n equals 1, the second is n equals 2, and we'll look at a transition that watches a final. The electron will end up at the third level. Okay, so that's an n equals 3. And we'll show that it started at an n equals 6. Okay, so it's going to spontaneously drop to a lower energy level. So n equals 6 as the initial, and n equals 3 is the final. So the question is, what is the change in energy associated with this? Okay, so what is the energy of the emitted photon for an atom that has an electron relax from n equals 6 to n equals 3. Okay, and we'll put the answer in joules. Okay, so to answer this question, we'll apply our Rydberg equation here. So it starts with delta E equals the Rydberg constant minus 2.179 times 10 to the minus 18 joules. And now we have our parentheses. So we're going to have the inverse of the final energy level. So we saw that it ended up at n equals 3. So that's going to be 3 squared, which is of course 9, minus 1 over the initial position. So that was 6 squared, which is of course 36. Okay, so after doing this, you should calculate that the delta E is going to be minus 1.816 times 10 to the minus 19 joules for the energy level. Okay, so notice that delta E, we've used this equation to show that the atom, represented here with the electron transitioning from n equals 6 to 3, is missing 1.816 times 10 to the minus 19 joules. So I'm highlighting here the minus symbol. So if the atom is missing this much, the energy of the photon that is emitted is going to equal the negative of this delta E. which means the energy of the photon is positive 1.816 times 10 to the minus 19 joules would be the energy of the emitted photon. Okay, so now we better understand the negative symbol. It's showing that when a photon is emitted, that we expect a negative sign for the delta E in the Rydberg relation, and that the energy of the photon is simply the opposite sign of that energy value. When an electron goes from a low n value to a high n value, we need the energy of that electron to increase, so a photon will be needed there, and so we would need an energy input. So we would have a positive value on delta E and a negative value for the energy of the photon, representing the idea that we would have to apply that photon to do work on the atom. Okay, so at this point, also remember earlier ideas where we've been able to take energy values like this, the energy of the photon, and think about the energy per mole by multiplying by Avogadro's number. Okay, so we could ask what is the energy value in a per mole basis. We could also even ask you to apply E equals hc over lambda and convert the energy into wavelength. So what is the wavelength of the light coming out associated with this transition? Or even calculate the frequency using this equation here. So be prepared to answer questions like